Alright, let's go. Number 10. Kepler 186f, the Infrared Eden. On April 17, 2014, astronomer Elisa Quintana and the Kepler mission team announced a discovery that would validate decades of theoretical speculation. 580 light-years away in the constellation Cygnus, they had found something humanity had long wondered existed, an Earth-sized planet, measuring 1.17 Earth radii, orbiting within the habitable zone of another star. Kepler 186f was the first confirmed world that proved Earth-sized planets in temperate regions around other stars weren't just possible, they were real. What makes this world potentially superior to Earth isn't immediately obvious from its specifications. The planet completes its orbit in 130 days around an M1V red dwarf star, receiving only 1/3 the stellar energy Earth receives from our Sun. At first consideration, this seems like a disadvantage, a frozen dim world perpetually locked in twilight. But here's where the conditions become intriguing. Red dwarf stars, like Kepler 186, burn their fuel so slowly they can remain stable for trillions of years, compared to our Sun's remaining billion years of habitability. While Earth faces an expiration date as our Sun expands into a red giant, any life on Kepler 186f could have geological timescales of stability our planet will never know. The dimmer radiation environment means less DNA damage from UV rays, potentially allowing life to thrive on the surface without the protective ozone layer Earth requires. But perhaps most fascinating is what photosynthesis would look like under a red dwarf's infrared heavy light. Earth's plants appear green because chlorophyll reflects green wavelengths while absorbing red and blue. On Kepler 186f, vegetation adapted to harvest infrared light might appear deep purple, black, or even actively light absorbing. If forests exist there, they would drink in wavelengths invisible to human eyes, creating landscapes that would appear alien despite potentially being more habitable than our own world. The first Earth-sized planet we found in a habitable zone might host life that thrives in permanent twilight, photosynthesizing in frequencies we cannot see. Number 9. TOI 700D, the Climate Chameleon. On January 6, 2020, Emily Gilbert announced TESS mission's first triumph at the American Astronomical Society meeting. The Transiting Exoplanet Survey satellite had discovered TOI 700D, an Earth-sized world just 101.4 light-years away in the constellation Dorado, at 1.19 Earth radii and receiving 86% of the stellar energy our planet receives. The number suggested a near twin to our world. But when climate scientists ran computer models of this planet's potential conditions, something unsettling emerged. They couldn't agree on what kind of world it actually was. Some simulations produced a planet covered in clouds and liquid water, with Earth-like oceans and rain cycles. Other models, using different atmospheric assumptions, generated a frozen snowball world with permanent glaciation. Still others predicted a dry, Mars-like desert with minimal surface water. The same planet with the same stellar energy input could be 3 radically different worlds, depending on its atmospheric composition, which we cannot yet measure. What makes TOI 700D potentially better than Earth is precisely this uncertainty. The planet represents the ultimate blank canvas for life or future terraforming. With the right atmospheric engineering, it could become an ideal water world, or a controlled dry planet, or a carefully regulated ice world with habitable zones in specific regions. Earth's climate evolved through billions of years of random chance. TOI 700D could be designed. The planet's 37-day orbit around its red dwarf star likely means it's tidally locked, with one hemisphere eternally facing the star and the other locked in permanent night. This creates the possibility of an everlasting twilight zone between the two extremes, a ring of perpetual sunset temperatures where conditions might remain perfect indefinitely, without the seasonal variations and ice ages that repeatedly brought Earth to the brink of total sterilization. Number 8. Gliese 667 CC, the Triple Star Sanctuary. In November 2011, astronomer Guillaume Anglada Escudé was analyzing radial velocity data from the HARP spectrograph when he detected something unprecedented. 23.6 light-years away in the constellation Scorpius, orbiting the star Gliese 667c, was a super-Earth receiving 90% of the stellar energy Earth receives. But this wasn't just another exoplanet discovery. Gliese 667c is the third component of a gravitationally bound triple star system, making this the first potentially habitable world ever found orbiting within a multiple star arrangement. What makes Gliese 667cc potentially superior to Earth becomes apparent when you consider the sky. If you stood on this world's surface, your primary sun, Gliese 667c, an M1.5V red dwarf, would appear orange-red and roughly 1.5 times larger than our sun appears from Earth, but you wouldn't experience the lonely isolation of Earth's single star. 2 additional stellar points would hang permanently in your sky. Gliese 6, 67a and b, a binary pair orbiting 230 astronomical units away. These wouldn't be mere stars in the night sky. They would be brilliant points of light contributing an additional 5% to the planet's total illumination, creating complex triple shadow effects and spectacular eclipse geometries impossible in our solar system. The planet's mass, approximately 4.5 times Earth's, suggests it could be a rocky super-Earth with enhanced plate tectonics, deeper oceans, and stronger magnetic fields than our world possesses. More intriguingly, the 2013 system analysis suggested as many as 6 or 7 planets orbit Gliese 667c, with multiple worlds potentially in the habitable zone. While subsequent reanalyses disputed some of these detections, arguing that stellar activity could mimic planet signals, even conservative estimates confirm at least 2, possibly 3 planets in the system. What remains unsettling is the gravitational complexity. How do planets maintain stable orbits over billions of years with 2 additional stars exerting periodic gravitational tugs? The system appears ancient and stable, yet our models struggle to explain its long-term dynamics. Perhaps this multi-star configuration isn't a disadvantage, but an advantage we don't yet understand. Additional energy sources, complex tidal forces driving geological activity, or gravitational interactions that maintain optimal orbital parameters through some mechanism we've never observed in our isolated single-star existence. Number 7. Proxima Centauri b, the Achievable Paradise. On August 24, 2016, Guillaume Anglada Escudé made an announcement that transformed humanity's relationship with space exploration. The Pale Red Dot campaign, using the HARP spectrograph at La Silla Observatory, had detected an Earth-mass planet, minimum mass 1.17 times our world, orbiting Proxima Centauri, the closest star to our Sun at just 4.24 light-years away. For the first time in human history, we had found a potentially habitable world close enough to reach. Every other potentially habitable planet exists at distances measured in dozens or hundreds of light-years, destinations that would require centuries of travel even at speeds far beyond our current capabilities. Proxima Centauri b orbits our cosmic next-door neighbor. The Breakthrough Starshot initiative proposes laser-propelled nanocraft that could reach the planet in 20 to 30 years, traveling at 20% light speed. Within a human lifetime, we could send probes to photograph this world's surface, analyze its atmosphere, and search for biosignatures directly. This isn't a distant dream for civilizations millennia hence. It's an achievable destination for missions that could launch within decades. What makes this proximity even more remarkable is what it means for colonization. While other habitable candidates might as well exist in other galaxies given our technological limitations, Proxima b represents humanity's first genuine option for interstellar expansion. The planet receives roughly 65% of Earth's stellar energy, placing it squarely in the habitable zone despite orbiting just 7.3 million kilometers from its star, far closer than Mercury orbits our Sun. But this closeness comes with consequences that transform the definition of habitability. Proxima Centauri is an active red dwarf that regularly unleashes massive stellar flares. In March 2016, observers detected a super flare that increased the star's brightness by 68 times for 20 seconds, bathing the planet in X-ray radiation 250 times stronger than Earth experiences and extreme ultraviolet radiation 60 times more intense. These flares should have stripped away any atmosphere billions of years ago, leaving a barren, airless rock. Yet the planet might possess something Earth cannot lose: proximity to human ambition and the certainty that whatever exists there, we will eventually visit it ourselves. Number 6. Kepler 442b, the long-term haven. On January 6, 2015, at the American Astronomical Society meeting, astronomer Guillermo Torres announced a discovery that challenged our assumptions about stellar longevity and habitability. 1,206 light-years away in the constellation Lyra, the Kepler Space Telescope had detected a planet with an Earth similarity index of 0.84, among the highest ever calculated. Kepler 442b, measuring 1.34 Earth radii with an estimated mass of 2.3 times our world, completes its orbit every 112 days in the habitable zone of a K5b orange dwarf star. What makes this planet potentially superior to Earth reveals itself when you consider not years or centuries, but eons. Our Sun, a G-type yellow dwarf, has perhaps 1 to 2 billion years of remaining habitability before expanding into a red giant that will vaporize Earth's oceans and sterilize our world. Kepler 442's host star, a K-type orange dwarf, will remain stable and habitable for 15 to 30 billion years, 3 times our sun's entire main sequence lifetime. K-dwarf stars represent what some astrobiologists call the Goldilocks zone of stellar types. They're more massive and stable than the flare-prone red dwarfs that bombard their planets with radiation. They're longer-lived than sun-like stars, providing vastly extended windows for life to evolve. They produce less ultraviolet radiation, creating gentler environments for surface biology, and their habitable zones are wider and more stable than those of either larger or smaller stars. If life arose on Kepler 442b at the same time as Earth, it has already existed for 4.5 billion years, with potentially 25 billion more years ahead. Time enough for civilizations to rise, fall, rise again, and achieve technological advancement beyond anything conceivable to our young species. Earth faces a cosmic deadline. Kepler 442b has only just begun its story. The planet receives 70% of Earth's stellar energy, suggesting a cooler climate that would require a thick carbon dioxide atmosphere to maintain liquid water. But this isn't a disadvantage, it's insurance. As the star gradually brightens over billions of years, the planet will warm naturally, maintaining habitable conditions far longer than Earth's precariously balanced climate ever could. What seems like a cold world now might be perfectly calibrated for maximum longevity, a world built for the truly long term. Number 5. Teegarden's star B, the ancient evolutionary advantage. On June 18, 2019, Matthias Siegmeister and his team at the University of Göttingen announced they had detected 2 Earth-mass planets using the Carmenez spectrograph. The system, just 12.5 light-years away in the constellation Aries, orbits one of the oldest stars in our cosmic neighborhood, an ultra-cool M7V red dwarf named Teegarden's star, estimated at 8 billion years old. Teegarden B, the inner planet with a minimum mass of 1.05 Earth masses, holds the highest Earth similarity index of any known exoplanet, 0.95. What makes this ancient system potentially superior to Earth becomes apparent when you calculate the timeline. Earth formed 4.5 billion years ago. Life emerged relatively quickly, perhaps within the first billion years, but remained microbial for 3 billion years before complex multicellular organisms evolved. If life on Teegarden B followed a similar pace, it has had 3 billion additional years beyond Earth's current evolutionary state. 3 billion years ago on Earth, life consisted entirely of single-celled organisms. The difference between then and now encompasses the entire history of complex life, from the first animals to technological civilization. The star's age means something even more profound. At 8 billion years old, this system existed before our sun even formed. If technological civilization arose on Teegarden B even 1 billion years ago, they would have had time to colonize every star system in the galaxy, spreading across the Milky Way like a wave expanding outward at subliminal speeds. Yet we detect no signals, no megastructures, no evidence of galaxy-spanning empire. The 2 planets, Teegarden B and C, both lie in the habitable zone, creating 2 simultaneous chances for life in this ancient system. The star is remarkably quiet for a red dwarf, with minimal stellar activity that could have allowed atmospheres to persist across billions of years. If life exists here, it may have evolved technologies and achieved understanding of the cosmos we cannot imagine. Or it may teach us the darkest lesson of all, that even with billions of years of evolutionary advantage in perfect conditions, technological civilizations remain silent, hidden, or extinct. Number 4. LHS1140b, the permanent ocean world. In April 2017, Jason Dittman and the Earth Project team announced the discovery of a super-Earth that would become one of the most studied potentially habitable planets. LHS1140b, orbiting 48.5 light-years away in the constellation Cetus, measured 1.73 Earth radii with a mass 5.6 times our world. The original measurement suggested an extremely dense rocky planet, 7.5 grams per cubic centimeter, denser than Earth itself. But in 2024, astronomer Charles Cadieux published a reanalysis that transformed our understanding of this world entirely. The new data suggested LHS1140b contains 10 to 20% water by mass, hundreds of times more water than exists on Earth. But this isn't a planet with Earth-like oceans scattered across continents. Computer models indicate that if the planet is tidally locked, as its 24-day orbit strongly suggests, all that water would freeze on the permanent night side while concentrating as the liquid on the star-facing hemisphere. The result? An eyeball planet with a single massive ocean approximately 4,000 kilometers in diameter, permanently positioned beneath the red dwarf's dim glow, surrounded by a ring of ice extending across the rest of the surface. What makes this configuration potentially superior to Earth is its permanence. Earth's climate zones shift with axial tilt, creating ice ages and warming periods that have repeatedly pushed life to the brink of extinction. Earth's continents drift, opening and closing ocean basins. But LHS 1140b's ocean would remain fixed in place for billions of years. A stable aquatic environment larger than the Pacific Ocean, bathed in constant low light, maintained at temperatures between 0 and 20 degrees Celsius. The host star is remarkably quiet, the lowest stellar activity of any known habitable zone planet host. No violent flares to strip atmospheres, no extreme radiation to mutate DNA, just steady, dim illumination that has remained virtually unchanged for billions of years. If life emerged in that permanent ocean, it would have existed in conditions more stable than any environment Earth has ever offered. The ocean might extend hundreds of kilometers deep before transitioning to high-pressure ice layers, a volume of liquid water so vast that Earth's oceans would be mere puddles by comparison. What forms of life could evolve in an ocean that never freezes, never boils, never moves, and exists under crushing atmospheric pressure we can barely imagine? Number 3. Kepler 452b, Earth's older, wiser cousin. On July 23, 2015, NASA held a press conference that captured global attention. The Kepler mission team, led by John Jenkins, announced they had found the most Earth-like planet yet discovered. Kepler 452b, located 1,800 light-years away in the constellation Cygnus, orbits a G2V star, the exact same spectral type as our Sun. The planet completes its orbit in 385 days, compared to Earth's 365, at a distance of 1.05 astronomical units. It receives approximately 10% more stellar energy than Earth receives. In almost every measurable way, this is Earth's orbital twin. But what makes Kepler 452b potentially superior to our world isn't similarity, it's maturity. The host star is 6 billion years old, approximately 1.5 billion years older than our Sun. If life evolved on Kepler 452b following a timeline similar to Earth's, it has had 1.5 billion additional years to develop. To understand this advantage, consider that 1.5 billion years ago on Earth, life consisted entirely of single-celled organisms. No plants, no animals, no complex multicellular life of any kind existed. The entire progression from simple cells to technological civilization occurred in less time than Kepler 452b's evolutionary head start. The planet's size, 1.5 Earth radii, places it in uncertain territory. It could be a rocky super-Earth with stronger gravity, more active plate tectonics, and deeper oceans than our world. Or it could be a mini Neptune with a thick hydrogen atmosphere and no solid surface at all. At 1,800 light-years distance, determining the planet's mass is impossible with current technology, leaving its true nature fundamentally unknown. What remains unsettling is what this world represents. A glimpse of Earth's future written in another star system's past. The stars entering the phase where it will gradually warm, eventually expanding and rendering the planet uninhabitable. The same fate that awaits Earth in 1 to 2 billion years. If Kepler 452b once hosted a thriving biosphere or technological civilization, they would have already faced the existential question Earth will someday confront. How does life survive when its home star begins to die? Number 2. TRAPPIST-1 system, the 7-world lottery. On February 22nd, 2017, astronomer Michael Gillen stood before the world's media and announced something unprecedented. Using the TRAPPIST telescope in Chile and NASA's Spitzer Space Telescope, his team had discovered not 1, not 2, but 7 Earth-sized planets, orbiting a single ultra-cool dwarf star 40.7 light-years away in the constellation Aquarius. 3 of those worlds, designated TRAPPIST-1, E, F, and G, orbit within the habitable zone simultaneously. What makes this system potentially superior to Earth is a matter of simple probability. Life on Earth represents a single experiment. One planet, one chance, one roll of the cosmic dice. TRAPPIST-1 offers 7 simultaneous experiments, all roughly Earth-sized, all orbiting close enough together that the entire system would fit within Mercury's orbit around our Sun. If the probability of life emerging on any given habitable planet is low, having 7 chances dramatically increases the odds that at least one succeeded. The proximity of these worlds creates conditions impossible in our solar system. From the surface of TRAPPIST-1e, the neighboring planets would appear 2 to 10 times larger than our moon appears from Earth. You could observe weather systems on adjacent worlds with the naked eye. Planetary transits would occur regularly as worlds passed in front of each other, creating spectacular eclipses. If technological civilization arose on any of these planets, they could reach their neighbors with 1960s level rocket technology. Interplanetary travel would be as achievable as our Apollo missions. Computer models suggest the 3 habitable zone planets might be water worlds, with liquid oceans comprising up to 5% of their total mass, 250 times more water than exists in all of Earth's oceans combined. But JWST observations in 2023 revealed something disturbing. The inner planets appear to lack thick atmospheres, likely stripped away by stellar radiation from their active red dwarf host. Did the outer habitable worlds retain their air? Are they ocean paradises or frozen airless rocks? The TRAPPIST-1 system represents the ultimate cosmic lottery. 7 tickets where Earth had only 1. But even with multiple chances, we still don't know if any won the grand prize of habitability, leaving us to wonder whether abundance of opportunity guarantees success, or if the conditions for life are so specific that even 7 Earth-sized worlds in habitable zones might all remain sterile. Number 1, K218b, the world that might already host life. On September 11th, 2023, astronomer Niku Madhusudan published data from the James Webb Space Telescope that may represent the most significant discovery in human history. His team had detected dimethyl sulfide, commonly known as DMS, in the atmosphere of K218b, a super-Earth 124 light-years away in the constellation Leo. On Earth, DMS is produced exclusively by biological activity, specifically marine phytoplankton and algae. No known abiotic process creates this molecule. If the detection is confirmed, we are not looking at a potentially habitable world. We are looking at a world that already hosts life. K218b was already remarkable before this discovery. In 2019, 2 independent teams detected water vapor in its atmosphere, the first time water had been definitively found on a planet in the habitable zone. The JWST observations confirmed not just water, but methane and carbon dioxide as well, creating a chemical profile consistent with what Madhusudan calls a Hycean world, a planet with a hydrogen-rich atmosphere above a global liquid water ocean. At 2.6 Earth radii and 8.6 Earth masses, this super-Earth receives stellar energy similar to what our planet receives, placing it squarely in the temperate zone where liquid water can exist. But the DMS detection transforms everything. This isn't speculation about where life could theoretically arise. This is a chemical signature that on Earth comes only from living organisms. The concentration detected suggests biological production on a planetary scale, an entire world's ocean potentially filled with life producing this telltale molecule. The signal remains at low confidence level, requiring additional JWST observations for confirmation. Scientists debate whether it represents genuine biosignature or instrumental noise, whether some unknown geological process could mimic biological production, or whether we're truly seeing evidence of an alien biosphere thriving on a world utterly unlike our own. What makes this potentially superior to Earth is the most profound advantage possible. K218b might have already solved the problem we're still trying to answer, whether life can exist beyond our planet. If confirmed, this Hycean world with its crushing atmospheric pressure and alien ocean chemistry hosts biology that arose independently, adapted to conditions we can barely simulate in laboratories, producing the same sulfur compounds that marine life creates in Earth's oceans. We wouldn't be alone in the universe. We would be late to a party that began long before we arrived.